Not every user of a single operating system should have the same level of access to files and directories. Like in a professional or enterprise level operating system, Linux has methods for securing file and directory access. This security systems allows the system administrator, the root user, or the file owner to protect their files from unwanted access or tampering by granting select user permissions to read, write, or execute files. For each file and directory, we can specify the permission status for the file's owner, for particular group of users, and for all other users. This is a necessity in a multi-user enterprise level operating system. The alternative will be quite chaotic. So in this lecture, I will show you how to check for and change permissions on files and directories for select users, how to set default file and directory permissions, and how to set special permissions. Finally, you will see how hackers' understanding of permissions might help them exploit a system. We have different types of users in Linux. As you know, in Linux, the root user is all powerful. The root user can do basically anything on the system. Other users on the system have more limited capabilities and permissions and almost never have the access that the root user has. These other users are usually collected into groups that generally share a similar function. In a commercial entity, these groups might be finance, engineering, sales, and so on. So in an IT environment, these groups might include developers, network administrators, and database administrators. So the idea is to put people with similar needs into a group that is granted relevant permissions. Then each member of the group inherits the group permissions. So this is primarily for the ease of administrating permissions and thus security. The root user is part of the root group by default, so each new user on the system must be added to a group in order to inherit the permissions of that group. So each and every file and directory must be allocated a particular level of permissions for the different identities using it. The three levels of permissions are here. I want to show you here. Are permissions read here, and we have W write here, write, and we have X here, X for execute. So read here, this grants permissions only to open and view a file. Write is this allows user to view and edit a file, and X is, as you know, this allows users to execute a file but not necessarily view or edit it. It is just execute if not written with read or write here. In this way, the root user can grant users a level of permission depending on what they need the files for. When a file is created, typically the user who created is the owner of the file, and the owning group is the user's current group. The owner of the file can grant various access privileges to it. So let's look at how to change permissions to pass ownership to individual users and to groups. So granting ownership to an individual user. To move ownership of a file to a different user so that they have the ability to control permissions, so we can use con here. I want to show you con. So this means change owner in Linux. So con, for example, Bob here, tmp Bob's file. Here we give the command the name of the user we are giving ownership to, Bob here, and this command grants the user account for Bob ownership of Bob's file. So granting ownership to a group. So to transfer ownership of a file from one group to another, we can use the CRAP. I want to show you here. CRAP. So GRP. So this is the change group command. Hackers are often more likely to work alone than in groups, but it's not unheard of several hackers or pen testers work together on a project, and in that case, using groups is necessary. So for instance, you might have a group of pen testers and a group of security team members working on the same project. The pen testers in this example are the root group, meaning they have all permissions and access. So the root group needs access to the hacking tools, whereas security folk only need access to defensive tools such as intrusion detection system IDES. So let's say the root group downloads and installs a program named new IDES. The root group will need to change the ownership to the security group so the security group can use it at will. To do so, the root group here will simply enter this command security new IDES. This is just an example, so I will not execute this command. So this command passes the security group ownership of new IDES. So now you need to know how to check whether these allocations have worked. So you will do by checking a file's permissions. So checking permissions. When you want to find out what permissions are granted to what users for a file or directory, use the ls command. ls command. Let me look at how many minutes we have. Yes. So use the ls command. Within the L here, this means long, switch to display the contents of the directory in a long format. So this list will contain the permissions here. So ls l command on the file user share hashcat, one of my favorite password cracking tools here in order to see what we can learn about the files. So this is the file type here, and this is the permission of file here. As you can see here, this is the number of links. So you will learn what is links. Link is in Linux. So this is the owner of the file, and this is the size of the file in bytes. So this means when the file is created or modified, and this is the name of file. So for now, let's focus on the seemingly incomprehensible strings of letters and dashes on the left edge of each line. They tell us whether an item is a file or directory and what permissions, if any, are on it. So the first character tells you the file type. The D stands for a directory, and dash indicates a file. So these are the two most common file types here. So the next section defines the permissions on the file. There are three sets of characters made of some combination of read, write, and execute in that order. So the first set represents the permissions of the owner, the second those of the group, and the last those all of the users. So regardless of which set of three letters you are looking at, if you see an R at first here, as you can see there are same, that user of group user has permission to open and read that file. As W is in the middle here, means that they can write to modify the file or directory, and the X is meaning if any X at the end means they can execute or run the file or directory. If any RW or X is replaced with a dash here, like that, then the respective permissions hasn't been given. Note that the users can have a permission to execute only either binaries or scripts. We can use the Linux command chmod or change mode to change permissions of the file or folder here. This is the command here we will use in this lecture. Only a root user or the file's owner can change permissions. In this lecture, we use chmod to change permission on hashcat.hc stat using two different methods. First, we use a numerical representation of permissions, and then we use a symbolic representation. Changing permissions with decimal notation. We can use a shortcut to refer to permission by using a single number to represent one RWX set of permissions. So like everything underlying the operating system, the permissions are represented in binary. So on and off switches are represented by 1 and 0 respectively. You can think of the RWX permissions as 3 on-off switches. So when all permissions are granted, this equates in a 1, 1, 1 in binary. A binary set like this is then easily represented as one digit by converting it into octal, an 8-digit number system that starts with 0 and ends with 7. So an octal digit represents a set of 3 binary digits, meaning we can represent an entire RWX set with just a one digit. This can be 0, 1, 2, 3, 4, 5, 6, 7, 8. 7 actually. Lastly is 7, not 8. So here I will create a table here for better understanding here. So in binary, here this is the binary here, octal, and I will show you here is the RWX. So the binary is 0. If binary is 0, 0, 0, octal is 0 as well, and RWX not read, nor write, nor execute here. So if binary is 0, 0, 1 here, octal is gonna be 1, and this can be not read, not write, but executable here. If binary is 0, 1, 0, and octal is 2, then this means this is the not readable but writable and not executable here. And if binary is 0, 1, 1 and octal is 3, then this means this is not readable but writable here and executable. If binary is 1, 0, 0, this means in octal 4, so this means this is not this is actually readable, not writable, nor executable. And if binary is 1, 0, 1, this means in octal is 5 here, and this is readable. This is readable, not writable, and executable here. And so readable, not writable, and executable. And here we have 6 and 7. Lastly, 1, 1, 0 is equals to 6 in octal by a system here, and this is the readable, writable, but not executable here. But if all binary is 1, 3, 1, 1, 1, 1, and this means in octal we have 7 here, and this is readable, writable, and executable as well. So using this information, let's go through some examples. First, if we want to set only the read permission, we could consult the table and locate the value for read. For example, this is the read permission, and this is the for. We can declare this using for or just a read, write, execute, or we can declare it in binary. Next, if we want to set permission to write and execute, we could use the same methodology and look for what set and what sets the W and what sets the X, which is executable and writable. So as you can see here, we have our WX here. So we want just writable and executable, and as you can see here, there's in octal, this is the 3. So in binary 0, 1, 1. So now we can pass an argument here where shortcuts come in. So for example, let's create a new file or dir here. Oops, my keyboard is actually okay. For example, touch here, example, oops, file. ls here. As you can see here, we created example file. This is not this has not inside anything. There's just a file with 0 bytes here. So let's declare ls la. As you can see here, we have example file here, which is created by Kali. So let's change this permission to c hash mode 774 hash actually example file. So ls la, and as you can see here, we changed these permissions here. So you should see rw here, rwx, rwx r here on the left side of this example file. So this confirms that this c hash mod call successfully changed permission on the file to give both the owner and the group ability to execute the file. So Linux use of permission to protect the users or groups, files, and directories from other users in the system can be used for offensive and defensive purposes. You should now know how to manage these permissions and how to exploit weak points in the security system, in particular SUD and SGID.